Hello, everyone. My name is Mohammad Keshavarzi. I'm a PhD student at the University of California, Berkeley. I'm so glad to have the opportunity to talk about our research on optimizing and manipulating mutual spaces in spatial computing interactions. So here we are in 2020, in the middle of an unfortunate pandemic crisis. The streets and highways of our busiest cities have become empty, as many of the countries are trying to contain the outbreak, while our indoor lives are fading away. A lot of us are trying to keep up with our everyday business by working from home and running remote meetings, classes, and conferences, and basically trying to communicate with our colleagues and friends and peers and loved ones. But I'm sure we all know and feel how different it is and or was to come together and gather in the same room rather than meeting everyone through a flat screen. So what is it of these in-person meetings that we're missing in our virtual 2D video conferencing? Let's just take a deeper look at this picture, for instance. You see, the enthusiasm, the facial expressions, the body gestures, these can all be captured by high quality cameras currently available in our video conferencing systems. But what may be missing is that all these fine qualities are encapsulated within a certain space owned by someone. We use it to express ourselves, like this little girl who is rising up to say something while also expanding her spatial ground. And in the end, we bring our individual spaces together and share it. You know, space matters. It also plays an important role in our professional meeting for important decision-making and negotiations, like this picture where a team scrambled around a table, sharing a mutual space while maintaining their own individual part of it. And you see by leaning forward and showing a strong body language, this man is using his space effectively, as if he wants to take a little more control of the social dynamics of the moment. So yes, mutual space matters, and mutual space is actually one of those critical qualities we cannot capture in current 2D video conferencing. And that brings us to the importance of exploring and utilizing spatial computing interfaces like augmented and virtual reality, which can theoretically maintain these mutual qualities in collaborative settings. This work, called holoportation, developed at Microsoft Research, is one of the many great examples of how mutual space can be preserved in augmented reality setting. Look how the presenter here, Shahram Izadi, steps back from his ground to allow his daughter to move around the table. I was personally very inspired by this work the day I saw it back in 2016. And it illustrated a very bright future on how telepresence systems can be utilized for remote communications. But if we just pause the video for a second, we do see some critical issues. First off, the amount of open space allocated for this experience in both rooms is pretty large. And if we take a closer look, we see some markers on the floor indicating that objects of these rooms, the chair and the table, were manually calibrated beforehand. But those settings may not be really feasible in our everyday spaces. To have large and accessible open spaces without any obstacles, and each time manually calibrating your surrounding furniture with each telepresent participant without knowing how the other spaces of those participants even look like. So it's fair to say, with our current real-world environments and surroundings, collaborative spatial computing has spatial limitations itself. So let me open this up a little more. Say we have three individuals wanting to hold a remote telepresence call with each other. User A in red, user B in yellow, and user C in blue. User A resides in this very large living room. You can see a perspective view on the left and a floor plan view on the right. User B, however, wants to join the telepresence from her small office. And user C is working from home and is planning to meet in his bedroom space, which has a little open area for the others to join. So let's look at the first problematic scenario where spatial collision occurs when participants show up in each other's spaces. Let's see how. Okay, this is user's A room, and he's hosting the meeting, which augments virtual avatars of users B and user C in an open area of his pretty big living room, with holding the same positional relationships with each other. In users B's space, however, she actually sees no one, basically no one. But if you look at the floor plan view on the right, the other two gentlemen are located outside her office. You see, when keeping the same positional relationships with each other, initiated in the previous scene, They just don't fit in user B's office. And more weird thing happens in user C's room, when user A is looking like a ghost stuck in the wall and dresser, while user B is also colliding with the furniture. Both remote individuals are in undesirable locations. Now you may ask, why do you need to keep the positional relationship constant? Why can't each user have the option to force position and manually identify a desirable location for remote avatars to be augmented in its space? So let's see what happens. Here we have the participants holding constant positional relationship with each other in all rooms. Now, let's just allow them to manually force position remote avatars in their own preference. So here's the problem. When user A is looking and talking with user C in his own room shown on the left, in user's B room, shown in the middle, the direction user A is facing is not quite right. Instead of looking at user C, it looks like user A is talking to the wall, and the line of sight is incorrect. This becomes much more abnormal in user C's location on the right, where user A is supposed to be facing at user C, but instead is looking at user B in a complete other direction. So how do we address this challenge? And this is where our contribution kicks in. Our first goal is to locate where users can walk and talk in their own room without colliding with objects in the other remote rooms. We do this by finding the mutual space between all rooms. Let's see how that works. Say we have 4 rooms with 4 individuals planning to remotely meet each other in a spatial computing settings. First, we perform semantic segmentation to determine the bounding box of each object in the room. Next, we intend to locate the standable spaces. Standable spaces are basically the volume of the room in which no object located within a human height is present. And the user movement can be performed freely without a risk of colliding an object in its surrounding physical environment. We calculate the standable space by simply subtracting the area of the object of which the object occupies in a room from the room itself. We do this with all rooms. Next, we define a rigid body function here called G, where theta describes a transformation vector. We then run a genetic optimization to determine the optimal theta of each rigid body motion so that the area of the overlap between the boundaries become maximum. Now, if we map the mutual space back to the room, shown here in a blue area, when all users stand and walk within the blue area of their own space, they are guaranteed not to cause virtual conflicts or line of sight mismatches within each other's spaces. Now, to add a little more flexibility and increase mutual usable spaces, we also define sittable spaces. Sittable spaces normally extend the standable spaces by adding areas where humans are able to sit on, such as sofas, chairs, and bed. Again, if we if we go through the same process, this time with sittable spaces, we observe larger mutual spaces, which users can stand, sit, and walk and move around those spaces without worrying to cause any unwanted collisions in remote rooms. Okay, so we wanted to implement our proposed framework on some real-world data sets just to see how it works. We chose a Matterport 3D data set for this, which includes a wide variety of residential houses with diverse styles and room functions. As you see here, the standable areas are indicated in green and the non-standable spaces are colored in red. And here on the right, the sittable spaces are visualized in yellow. Again, green showing the standable space and red will be the non-standable space. Moving on to identifying the mutual space between multiple rooms, this illustration shows how our genetic algorithm is gradually improving the results and expanding the mutual area in higher generation values. And here we show the mutual ground in blue after 40 generations of the search between these rooms. But then the question arises, what if we need more mutual space? What if it's just not enough and the identified mutual grounds are small, too small for the remote communication purpose? Say you want to play a game or inspect an object between participants where the object doesn't fit the mutual boundary. What do we do? So that brings us to our second goal, which is rearranging the furniture so that we increase the mutual space while minimizing the overall effort to do so. So the effort of each move is basically calculated by multiplying the distance of the object's translation by the object's width. So in simple terms, moving a bed is considered to have a higher effort value than moving the chair for the same distance. So again, our goal is to slightly manipulate the room layout to increase mutual space with minimum effort. To simplify this process for the user, we define increased steps, where each step has the goal to achieve 10% additional mutual space from its previous step, while maintaining the effort to do so, while maintaining the minimum effort to do so. Now, let's take a look at how the furniture manipulation system works in an example. Again, we use real-world data sets from the Matterport 3D scenes for this experiment. We have a family room, an office, and a bedroom. First, we extract the standable and non-standable spaces using the methods previously explained. Next, by utilizing our proposed mutual space identification system, we can locate the maximum mutual ground between these three rooms. We then use a strength Pareto evolutionary solver to run the optimization for the two objectives. Effort, which is shown on the vertical axis, and the mutual area, which is on the horizontal axis, which we want to increase. So when we plot the rearrangement solution space, we can find the initial arrangement point on the Pareto frontier with the e-value of 0. Then, by increasing the area in each step, we find the rearrangement solution which satisfies the increased area goal and holds the lowest effort value in that step. And as you see, after 5 steps, we significantly increase the mutual space between the rooms while minimizing the effort required for the furniture rearrangement. Finally, to have a better understanding on how users would experience the system's output, we deploy our proposed method on a Microsoft HoloLens as an augmented reality visualization. For the target spaces, we scanned our office area at Berkeley and chose a conference room, a kitchen, and our main laboratory space for our experiment. We also provided the bounding boxes and semantic labelings for the model. The system then calculated the standable and open spaces, visualized here in green, and the mutual spaces seen here in blue. Here you see the view of the HoloLens in the kitchen. We visualize the mutual space boundary with an offset of 47 centimeters of the ground so the users can clearly relate to it. And here you see the main laboratory itself. Again, the blue areas indicate that you can freely move around in this boundary without causing any conflicts in other rooms. Finally, a floor plan view of the space with different screenshots taken in different locations from the HoloLens headset. So, limitations. Of course, there is limitations to our work. First off, in our current version, the crescent steps may not have any continuous relationships with each other. For example, in step 1, you might be moving a chair in a certain direction to achieve minimum effort. But if you then decide to move to step 2, it doesn't take into account step 1's transformation. The next limitation is that our system doesn't automatically take fixed position objects into account and should be defined manually. We also currently use generic data provided by moving companies to estimate a weight of an object given its type. However, objects from a same type may have various weights, and therefore it would be important to integrate correct values to achieve more accurate results. And finally, our future steps. We definitely want to perform more extensive user studies. We also hope we can develop this tool for cross-platform AR/VR interfaces and also use more robust floor planning methods for the furniture manipulation. And with that, I guess that's it. Thanks very much for listening, and please feel free to share any questions. Thank you.